Welcome back. This is the part of the course where we start getting our hands dirty with the core concepts of data analysis. Now, keep in mind that data analysis is not an exact science. In fact, you could also call it an art. What we're going to go through is a process of performing data analysis. Note that this is not the one and only process. As you get more experience, you can come up with your own personal process which serves your needs for a specific project or a specific application. But as you might have realized by now, data analysis contains a lot of topics and concepts. So understandably, it's difficult to come up with a one size fits all solution. Therefore, we are going to define a skeletal framework that helps us get started. The particular framework that we are going to look at is a distillation of the experiences of many data scientists and many organizations as well. We broadly divide data analysis into three categories of analysis, namely univariate, bivariate, and multivariate analysis. Univariate analysis refers to analysis that we apply on a single variable. That's what univariate means. It's a single variable. Similarly, bivariate analysis refers to analysis of a pair of variables which are being analyzed simultaneously. And finally, multivariate analysis is analysis which is simultaneously performed on a larger set of variables. The advantage of having this framework is that it is incremental. As in, once we know the range of possibilities of what can be done with a single variable, we can generalize it to a pair of variables and then to multiple variables as well. Now, I have used the word variable many times so far. Technically, a variable is any quantity that varies. More specifically, in the context of tabular data analysis, a variable is any column of your data that has more than one unique value. Because if a column has exactly one distinct value, then it's not a variable, it's a constant. So again, to reiterate, a variable for us is just a column. The same concept is referred to in different domains with different names. In the context of, say, machine learning, you might say that a variable is a feature. In the context of databases, you might call it a column or a dimension. It's likely that we might use all of these terms, features, columns, variables, dimensions, interchangeably. But whenever we use a new word, its meaning should be apparent from the context. So let's start with univariate analysis. As discussed, uni means one and variate means variable. So univariate analysis is the analysis of a single variable. To begin with, we must understand the different types of variables. There are three major types of variables: numerical, ordinal, and categorical. Let's begin by understanding what a numerical variable is. Well, simply put, a numerical variable is any column that contains numbers. But the catch is that these numbers have to have an inherent meaning. That is, the values of the numbers should represent actual measurements of things. For example, let's say we were trying to make a fintech application which helps us determine if an applicant is eligible for a loan. Now, one of the features we would want to measure is the annual income of the applicant in, say, Indian rupees. This would be a numerical variable since the values in the column have an inherent meaning. For example, let's say we were trying to make a fintech application which helps us determine if an applicant is eligible for a loan. Now, one of the features we would want to measure is the annual income of the applicant in Indian rupees. This would be a numerical variable since the values in that column have an inherent meaning. In other words, the numbers directly represent whatever it is that we want to capture. On the other hand, if we were to look at another column which would contain, say, the phone numbers of the applicants, that variable would not be a numerical variable even though it looks like a number. Because the numerical value of a phone number means absolutely nothing, it's just a code. So numerical variables can take any value along the number line. That's also why they are called continuous variables. Basically, if we were to plot a numerical variable on a graph, we'd see a continuous line. There would be no gaps because numerical variables can take on any value in a given range. If there are gaps, that means that there exist some values which are impossible for that particular variable to occupy. These would not be continuous, of course. Finally, the most important characteristic of numerical variables is that they support arithmetic operations. Imagine that you're working for a cargo company and you have a data set that contains the weights of the different packages that you are trying to deliver. Now you can calculate the sum of these weights of all the packages, maybe to determine what kind of vehicle you should use for delivery. You can also take the average of the weights. Now imagine that there's another column which lists the pin codes to which each package must be delivered. Here you cannot do any arithmetic. Adding pin codes means nothing. There is no such thing as an average pin code either. So that's an important characteristics. If you can do meaningful arithmetic on a column, then it's a numerical variable. Before we move on, here's a question for you. In the table shown here, which is the numeric column? Feel free to pause the video right now and think about it. So the numerical column is the first one, duration in seconds. It is the only column which has numbers with an inherent meaning. The age column, as you can see, also has numbers, but they are ranges of age, not the actual age. The next type of variable we need to consider is called an ordinal variable. These variables are those that are not continuous, but they can be ordered. That is, there exists an order relationship between the different values of the variable. So just like numerical variables support the four fundamental arithmetic operations, ordinal variables support order relationships like greater than, less than, equal to, less than or equal to, or greater than or equal to. Thus, it follows that all numerical variables are also ordinal variables, but not all ordinal variables are numerical variables. Sometimes for for specific order relationship may not be apparent and it has to be imposed by the analyst. For example, suppose we were performing sentiment analysis and we have multiple pieces of text which we want to classify into three sentiments: positive, negative, and neutral. Now, these three sentiments are just arbitrarily defined groups, but we can impose an ordinal relationship on them, which is like saying that positive is greater than neutral and neutral is greater than negative. Defining this relationship is often up to the analyst, depending on the application. So here's a question again. In the dataset shown here, which is the ordinal variable? Pause again here to think about the answer. Well, we have already decided that duration is a numerical variable in the previous slide, and therefore it is an ordinal variable. But which other variable is an ordinal variable? Well, the answer is age. We can see that age here is not a number, but a range of numbers. What this figure means, 20 to 24, what that figure means is that this person's age lies somewhere between 20 and 22 and 24 years of age. Similarly, we have a bunch of other ranges. These are not numbers in themselves, but they can be ordered. The last type of variable we need to understand are categorical variables or nominal variables. These are neither numbers nor orderable entities. They are just independent groups. These are also known as discrete variables. In contrast with continuous variables, which we have seen before, categorical variables cannot take just any value. Their values must come from a predefined set of values, like phone numbers or pin codes. Unlike numerical or ordinal variables, they support only two operations, that is, inequality or inequality. And the only thing you can do with them is count them or use them to group or filter different rows in your table. Given that, can we find out which are the categorical variables in this dataset? Pause the video now and think about the answer. So the categorical variables here are gender and country. Both these columns can take values which belong to a specific set of values. They are not numbers and there doesn't exist any order relation among their values. By the way, please do not make the mistake of assuming that gender is an ordinal variable. So that concludes our discussion on the type of variables. Figuring out the types of variables is a fundamental building block of data analysis process. Whenever you see a new data set, take a few minutes to go through your columns and determine their types. Because depending on these types, you will be able to figure out what operations you can perform on the different columns of your data set. Now that we know what kind of mathematical or logical operations we can perform on the columns of our dataset, Let's take a look at what we can do with these operations to get a very broad, general idea of the behavior of our data. The question we are trying to answer is this: for a given column or a feature in our data set, can I quantify its behavior using a smaller set of numbers? These numbers are essentially what are called summary or descriptive statistics. To motivate summary statistics, imagine this scenario. Let's say that you are an astronaut who is stranded on a strange planet and you're waiting to be rescued. Now, your organization can mount a rescue mission for you, but in order to do that, they need some information. Specifically, they need to answer three questions. What is the length of the day on the planet on which you're stranded? How is the weather there? Is it cloudy, hot, or cold? And what is your heart rate? Well, that sounds easy enough, but here's the catch. Your transmitter is broken. It has a bandwidth of only 128 bits, and you can use it only once a week. In other words, you can only transmit 128 bits of information once a week. So the problem you have to solve is as follows. Which 128 bits of information would you transmit in order to effectively answer these three questions? For some context, note that it takes anywhere from 8 to 64 bits to transmit an integer and anywhere from 32 to 128 bits to transmit a floating point number. Do pause the video here and think about this problem for a while. Well, the very first thing you need to do in order to answer these questions is start collecting data. You're a data analyst after all. So let's say that you have collected a week's worth of data because your frequency of transmission is once per week, which looks like this. So the data that you have collected looks something like what we have collected in this table over here. Every day you make a note of whether the weather is hot, cloudy, or cold. Every day you measure the length of the day in hours and you record it. And then you also record your heartbeat at the end of every day. So now your communication problem translates into this statistical problem. How do you summarize this data so that you are least wrong? How do you measure the error? And how do you minimize that error? So you see, summary statistics is all about communication effectively. How do we effectively compress a set of numbers into a single number or at least a small set of numbers so that that number can act as a good proxy for the set of numbers that you're trying to communicate? And someone at the other end, when they receive this compressed set of numbers and use it to make guesses about your data, they are least wrong. So let's try and build our way towards a solution. Let's say that every column here is being summarized by a single number, which we'll call S sub I. I here is the position indicator for a given column. That is, since we are trying to summarize these three columns, S sub 1, I would go from say 1 to 3. Therefore, we would have three summary numbers, S sub 1, S sub 2 and S sub 3. Now for any column I, we say that S sub I is a good summary if the discrepancy between S sub I and each value of the ith column is small. Note that we are trying to summarize the whole column with a single number. Therefore, each value in the column is going to produce its own discrepancy with the summary number. That means that every row is going to create some error with S sub I, right? We then have to figure out a way of combining these errors over the whole column. And if that aggregated error is small, then it means that we have a good summary statistics. Otherwise, if the aggregated error is large, we have a bad summary statistic. If we try to lay down this process with a little more mathematical formality, this is what it looks like. The purpose of this slide is just to gently introduce some mathematical notation. It's perfectly fine if you don't understand this at first glance. Rest assured that this will get clearer with time and practice. So we have decided that I is the position indicator for a column and S sub I is the summary indicator for the ith column. Let's introduce another positional indicator J, which indicates the row position. So now each value in the table can be denoted as I sub X sub Ij. That is the value at the ith row and the jth column. So now for a given column I, we have a single summary statistics S sub I and the set of values in that column X sub ij. And each such value is going to create its own error against X sub I. And our intuition tells us that if any X sub ij is close enough to X sub I, then the error must be low. If it is very far away, either too less or too greater than S sub I, then our error must be large. So now the question boils down even further. How do we measure the error if the absolute value of the difference between the X values and the S values is greater than 0? By the way, we are interested in absolute values because the sign of the error does not matter. Whether the error is positive or negative, it's still just as bad. So here we are going to introduce three different strategies of defining errors. In each of these graphs, our guess of the summary statistics is on the x-axis and the error is on the y-axis. Let's look at the first graph here. Effectively, what we are saying is that no matter what your guess is, there will be exactly one value for which the error is 0. There will be exactly and only one correct value. For all other values, the error is 1. Essentially, there are only two values of error, that is 1 and 0. And the value of 0 can only be reached if you make the exact correct guess. In the second graph, what we are trying to say is that as you move away from the correct value, whether to the positive side or the negative side, the error increases in direct proportion to how far away you are from the correct value. The farther you guess, the more the error. Then finally, in the third graph, we are saying that as you move away from the correct value, either to the positive side or to the negative side, the error increases in proportion to the square of the distance between your guess and the correct value. Again, I should emphasize that these three are strategies for measuring error. You can pick any one of them as and when you like, but depending on these curves, these errors will have different behaviors. In fact, the first graph corresponds to what is known as mode. Simply put, the mode of a column is the most frequently occurring value in that column. And essentially what we are saying is that if we pick this strategy for defining errors, then the errors will be minimized at the mode of the dataset. At exactly the value which corresponds to the mode, you will have the minimum error. And for any other value, no matter how small or how large, we will have the same error. So there is no notion of greater error or lesser error. There are only two values of error, one corresponding to the right summary and the other value to all the wrong summaries. You can probably already guess which type of variable this corresponds to. The next graph corresponds to the median. If you arrange values in a given column in an increasing or a decreasing order, and then the value which is found at the exact center of this sequence is called the median. By picking this strategy, we are saying that the error will be minimized at the median of these values. And then the last graph corresponds to the mean or the average. It's simply the sum of the values in a column divided by the length of that column. And by picking the strategy, we are saying that the error will be minimized at the mean of that particular column. So we have three strategies of defining errors, which give us the mode, median, and the mean respectively. Together, these values are the most important univariate metrics. To test your understanding of the mean, median, and mode, try to think about this question. Which error applies to which column? Note that weather is a categorical variable, day length is a numerical variable, but it changes very slowly. You see that it doesn't change very drastically. Heartbeat is also numerical, but it may change very drastically. Naturally, it's heartbeat. Feel free to pause the video here and think about this. So let's take a look. The first column, weather, is a categorical variable. So we are going to apply mode to this one. Clearly, median and mean don't apply to this column because it has no concept of ordering or difference between values. Remember that categorical variables only support equality and inequality. The next column is the day length. It is numerical. So we can apply either mean or median to this column. But we have also noted that this is a slowly changing column. That is, we have values that are very tightly grouped around its center. For example, you are not likely to find that for a few days the length of the day was 9 or 11. or 10 hours, but then suddenly jump to 14 hours. In other words, this is not a variable that is likely to have any outliers. And as we've seen in the error graphs earlier, if we have outliers and we apply the mean, we will see massive errors because the error corresponding to the mean changes by the square of the difference. So even for a small error, we are likely to get penalized a lot more. Then the next column is heartbeat. This is also numerical, so we can apply either mean or median to this column. But note that this can change very drastically. In other words, we are more likely to find outliers here. If we apply mean here, we will have really large errors. Median, on the other hand, is robust against outliers. That is, even when a variable has outliers, the median produces a reasonable summary statistic. So now that we know the three fundamental summary statistics, let's go a step ahead and look at the next two. They are called variance and standard deviation. Let's take a look. The variance of a column is essentially a number which tells us how much a variable spreads around its average value. A high variance literally means high variability. By itself, it doesn't mean much, but it is very useful when comparing two different variables. So we'll see examples of this later in bivariate analysis. Here's an example. We see here three different histograms denoted by these three colors. They represent the length of the day on Earth during the months of May, June, and July over the last 3 years. So we can see that the orange histogram, which corresponds to May, has its center around something like 12.75 hours, which means that the average length of day in May for the last 3 years was around 12 hours and 45 minutes. Similarly, if you look at July, it was around 12.85 hours, and in June it was around 13 hours. So the days were on average longer in June, which is surprising. June is when summer usually changes into monsoon, so the peak of the length of day should come in May, not in June. But anyway, if we look at the width of these histograms and say that, this is the data corresponding to May, it has a fairly large width. Then there is this purple histogram corresponding to July, which has a very large width. And then there is the small set that corresponds to June, which has a very small width. So if we look at the width of these histograms, we get an idea of the variance of these values. And here things get even more interesting. There is a lot of variance in May and July, but in June, the length of the day is not only higher on average, but it has much less variance. This means that in May and July, you will see a lot of variation in the length of the day, but not so much in June. What we're doing here is looking at graphs and qualitatively commenting on what the histogram tells us. The mean and the variance are statistical univariate measures, which gives us a very mathematical, quantitative way of making the same assertions. So if we were to take the means and variances of these variables and compare them, we would have arrived at roughly the same conclusions. Finally, for the sake of completeness, here's how you calculate the variance. Let's say that we are talking of the ith column, then what we do simply is take the mean of that column, which is denoted with mu sub I. We subtract that from the original data or the whole column, because ultimately remember that the variance, the point of variance is to measure the spread of the data centered around its own center or around its own mean. So that's why you have to subtract the mean, and then we square up the values and we average them. So that's how broadly you calculate variance. Don't worry about the math too much right now. Most of these formulae are going to be pre-implemented in whatever tool we use next. So we will have a much more direct impact on, we'll have a direct implementation of how we can use them. So the next univariate metric we consider is the standard deviation. It is simply the square root of the variance. Now you might ask, if it's just the square root of some quantity we already know, then what's the use of it? Actually, the standard deviation is useful because it has the same unit of measurement as your variable. Note that when we calculated the variance, we were performing a sum of squared values as is shown here. So in this case, say we are measuring the length of day in hours, then the variance would have the unit of hours squared, whereas the standard deviation would still be in hours. So that's a much more useful value to have when you're comparing with the original data. Secondly, standard deviation is important when trying to quantitatively detect outliers. Here's the length of day data from the last 3 years for all months. The black line is the mean of this data. The blue lines are basically mean plus 1 standard deviation and mean minus 1 standard deviation. And the green lines are mean plus 2 standard deviations and mean minus 2 standard deviation. Now let's say that we are collecting more and more length of the day data and we want to figure out if the behavior of the new data is as expected or are we seeing something surprising. Well, if the new values fall between the mean and the first standard deviation on either side, then we conclude that there is nothing really surprising. If they fall between the first and the second standard deviation, like here or here, on either side, then we say that the values are moderately strange. But if we say that they are more than 2 standard deviations away, that is either above this green line or below this green line, then we say that they are definitely outliers. So that's a quick and convenient way to judge whether some value is an outlier. Now, so far, we have seen only mathematical ways of doing univariate analysis on our data. We have a column, we apply some formula on that column, and we get a single number out. That number can be the mean, median, mode, variance, or standard deviation. But ultimately, these are just numbers. They do have a very strong mathematical quantitative meaning. But even to the best trained analyst, beyond a point, sustaining a purely quantitative understanding of data becomes very difficult. The alternative approach is to look at the data graphically. So let's talk about the two most important graphical tools of univariate analysis, histograms and bar charts. So here we have 4 columns. We've already seen this data before. And we have corresponding to these columns a histogram and a bar chart. Let me start with a question right away. Which is the histogram and which is the bar chart? And once you've figured that out, try to think about which column the histogram corresponds to and which column is represented by the bar chart. Feel free to pause the video and think about this. So the figure at the top is the histogram. Histogram is essentially created by taking a column, in this case the duration column, identifying its range, that is the maximum and the minimum values in it, dividing the range equally into a number of bins, and then counting how many values lie in each bin. So that's what we have done here. We've taken the minimum value, which is 0, and we have taken the maximum value, which is 165,000, or it's 16,500, and we have divided it equally in a bunch of bins, and the length of these bars or the height of these bars, it simply represents how many values fall in that particular range. And note that these bins are continuous. That is, the end of each bin coincides with the beginning of the next one. So from this histogram, we can tell that most of the values in this column lie in the second bin. And if you look carefully, you can see the edges of this bin. So basically what we are saying is that most durations of seconds lie between 660 seconds and 1320 seconds, which is 10 minutes and 20 minutes, 11 minutes and 22 minutes roughly, right? A bar chart, on the other hand, is just a number of independent values which are plotted next to each other. There is no necessary relation between the different bars. They are just compared by their lengths. In this case, the bar chart is this figure at the bottom and corresponds to the counts of the values in the country column. So for each unique country occurring in this column, we create a bar, and the length of that bar corresponds to how often that country occurs in that column. So we can see from this slice of this data set that France occurs twice, India occurs thrice, Germany and Australia both occur only once, and the United States also occurs twice. So that we just carry on this process for all unique countries throughout the data set, and that's how we build a bar chart. Broadly, there are a lot of things that we can infer from histograms and bar charts. For one, we can simply see the shape of the data. And this is important because it can tell us at a glance whether the data peaks around a certain value or whether it peaks at all, how much it spreads, etc. You can see the distribution in a lot more detail. For example, we can see from the histogram that there are a lot of values which are in the early part of the graph. But there are also some values, I'm not sure if it's completely visible, but since the histogram stretched up to this point, we can be sure that there are also some values which are very few in number, but they are there. And of course, we can see outliers. We can see that these are some of the outliers, or in this case, these are the outliers. Note that histograms are used for continuous or numerical variables, and bar charts are used for discrete or categorical variables. And with that, we conclude our discussion on univariate analysis. We saw that we have a bunch of different statistical and graphical tools at our disposal when we want to study one particular variable at a time. Next, let's try and generalize these approaches to two variables. This is nothing but bivariate analysis. We are simply going to take whatever we know already and apply it to two variables instead of one. However, there are multiple combinations of variable types we need to consider. When doing univariate analysis, we were able to figure out the type of variable and apply certain methods accordingly. Here, we have to deal with combinations of two types. Specifically, or two combinations or two variables could be both continuous, or one of them could be continuous while the other was discrete, or it is also possible that both of them are discrete. So let's take a look at what we can do. When it comes to the first case of bivariate analysis where both variables are continuous, one of the most powerful graphical tools we have is a scatter plot. We simply plot one variable on the x-axis and one on the y-axis, and each point, each data point, that is each row of your table, is represented by a dot on the xy plane. So this particular chart that you see here is essentially a scatter plot of the heights and weights of about 1,000 individuals. So every point on this particular graph represents an individual, and they have a certain height in inches and a certain weight in pounds. So what we have here, and by the way, the color represents gender. So you can probably guess which one is male and which one is female. The green line in this case, actually in both cases, is the best possible straight line fit that we can draw through this data. We can ignore the green line for now. This is basically an example of what we would learn when we go over to regression. What this means is that we have a data which contains 1,000 rows and two columns. One column is height, one column is width. We simply take each row, find the height, find the width, and use them as the XY coordinates of where that particular dot should lie on the graph paper. That is broadly how you draw a histogram. That's how we draw a scatter plot. Similarly, we have another scatter plot from a very well-known data set that is used in machine learning called the Boston Housing Prices dataset. It essentially contains the details of a bunch of different houses and their prices. So it's a regression task. The idea is given a bunch of different attributes of a particular house, can you predict its price? And one of the attributes that is included in that dataset is the average number of rooms. So we can see that there are outliers, of course, but in general, there is an increasing trend. As the number of rooms grows, the price grows. That makes sense, right? You can see that scatter plots make it very obvious, at least graphically, whether there is any linear trend or correlation in the data. This is important because finding links between variables is one of the most important jobs of a data analyst. The commonest questions that we get are usually of the same format. What explains sales? What explains profit? What explains loss? What explains revenue? What explains customer churn? What explains the spread of a disease? And so on. If you're lucky, whatever you're trying to explain will have a linear trend with some other variable. And you can say that the other variable explains it. So for example, what explains my weight? Well, height could explain my weight. As you grow taller, you grow heavier. Or what explains price? Well, average number of rooms explain the price. Why is a particular house more expensive? Because it has more number of rooms. Of course, in practice, it is rarely that easy. But linear relationships, or basically correlation between variables, is a fundamental idea in data analysis. Scatter plots are an easy, qualitative, graphical way to see these relationships. Now that we know what correlation graphically looks like, let's take a look at its mathematical formulation, just again for the sake of completeness. Note that none of the formulae we have seen so far are super important. These metrics are already implemented in whichever tool we use, Excel, Python, Tableau, whatever. So you may not have to use them every day, but it's always important to know what's happening under the hood. So correlation is basically a measure of statistical dependence. It is defined or for a pair of continuous variables, and this is broadly how you calculate it. Let's say that x and y are my two variables or two columns in my table. Then rho x comma y is basically the symbol that we use for correlation, and this is how it's calculated. Mu of x and mu of y are the means of the x and y columns. I take the column x, and from each row of that column, or basically from the whole column, I subtract the mean of that column. From y, I subtract the mean of y, and then I multiply those two columns together. For each, basically, it's what is called an element-wise multiplication. Each row is multiplied with the other row, and then we take the average of this product. And here in the denominator, you see sigma x and sigma y. This is nothing but the standard deviation of x and y. So we know x, we know y, we know how to calculate mu of x, we know how to calculate mu of y. We also know how to calculate sigma of x and sigma of y. And we also know how to do all of this arithmetic, and therefore this E, by the way, stands for expectation, which is also another word for average. So we know how to calculate averages. So that's why calculating correlation is straightforward. Before we proceed, let's take a look at these four charts. They are called the Anscombe quartet. We have four different scatter plots corresponding to four pairs of continuous variables: x1, y1, x2, y2, x3, y3, and x4, y4. Now, what is funny about these four pairs of variables is that even if their scatter plots look drastically different, their correlations are actually exactly the same. You can actually figure out the values, the axes are given, and you can do the math. The scatter plots look very different, but if you calculate the correlation, they're actually exactly the same. The point here is that the quantitative value of correlation alone can be sometimes misleading. So whenever possible, look at the plots as well. And by the way, if you want to get a good feel of what correlation is like, play this game. It's called guessthecorrelation.com. It's a fairly interesting game. So maybe I could just show you a couple of things. Let's mute this tab first because it's likely to make some noise. So what we see here is an x-axis from 0 to 1 and a y-axis again from 0 to 1. And there is a bunch of data which is randomly scattered. I don't see any linear trend. I don't see anything that sort of dictates the relationship between x and y. So I'll say there's no correlation. So I'm just going to say 0. And if I press enter, it basically cost me a little bit. The true correlation was 0.12 and I guessed 0.00. So, I was not very wrong, but just a little wrong. Well, you can see that there is some correlation here. So I would say something like 0.3, because you can see that maybe there is like a increasing trend. And yeah, that was better. It's at least less error than last time. The true R is 0.2 and I guessed a 0.3. This is again similar, like it pretty much looks random to me. So I'm just going to say 0.05 or something. Oh, I'm getting better at this. You see, now the true R was 0.03 and my guessed R was 0.05 and the difference is 2. So feel free to play around with this game and see where it lands you. So let's continue. I hope you enjoyed the game. Now that we know how to do bivariate analysis when both our variables are continuous, let's take a look at what we can do when one of our variables is a discrete or a categorical variable and the other one is continuous. The most common process to deal with this kind of a pair is grouping and aggregation. The discrete variable that we have is called, in this case, a dimension, and the continuous variable in this case is called a metric. So essentially what we do is we group values in the metric by every unique value found in the dimension, and then we apply some sort of operation on these groups. This operation is called an aggregation. Some common types of aggregations are the sum, the average, the minimum and the maximum, and many other things. So here's an example of how grouping and aggregation works on the Fisher-Iris dataset. As we have seen before, the dataset contains 5 variables or columns. There are 4 columns which are sepal length, sepal width, petal length and petal width, which are the 4 numerical columns. And the 5th categorical column is the species, which contains 3 unique values, which are Virginica, Versicolor and Setosa. Those are the 3 individual species of virus that are recorded in that particular data set. So then the species column becomes our dimension, and we can pick any of the 4 numerical columns as our metric. So let's pick, say, petal length as an example. We filter the petal length column in our data by each value which is present in our dimension. So we have 3 groups of petal lengths, each corresponding to 1 unique value found in our dimension. So what we do is we select all the rows where the species is Setosa and take out the petal length column. We select all the rows where the species is versicolor and take out all the petal lengths. And then we do the same thing for virginica. Then for each of these 3 groups, we simply average the petal length. You can see the result over here. What this means is that the average petal length for a Setosa is much lower than that of versicolor, and which itself is much lower than the average petal length of a virginica flower. Now you see the dimension we picked was the species, the metric we picked was petal length, and the aggregation we picked was the average. You can pick any combination and see which combination reveals a pattern. In fact, this is the same process that later generalizes into machine learning. So the way we would use this sort of a heat map would be, if say a record for a new flower comes in, we basically say that, okay, what's the petal length? And depending on which average it is the closest to, we can assign a particular label. And of course, we can do the same with other things as well, all of the other dimensions of that flower. So this is broadly how you deal with bivariate analysis when one of your variables is discrete and the other is continuous. The next question we will need to answer is what to do when both variables are discrete. Well, unfortunately, there's not much we can do. As you know, discrete variables only support counting. So at best, we can simply count how many times a unique pair occurs in our dataset. This is also known as cross tabulation, and we will see this in a lot more detail in one of our upcoming videos. So that wraps up our discussion on bivariate analysis. And as before, multivariate analysis is simply a generalization of univariate and bivariate analysis to multiple variables. There are many algorithms and processes that fall under the umbrella of multivariate analysis. In the interest of brevity, we will not go into their algorithmic or mathematical detail, but let me mention that regression and principal component analysis are the 2 most popular multivariate analysis techniques. In general, the field of data analysis is very loosely defined. Employers, interviewers, colleagues can throw any algorithm at you, and you may not necessarily be able to say that a particular algorithm does not fall under data analysis. So unfortunately, you cannot stop learning. But what we have covered so far is the fundamental process of data analysis. If this is done properly, you will not have to do much else. And even if you do, you will still have a solid conceptual understanding of this process, which you can recommend to your clients and your colleagues as well. In the next video, we are going to get our hands dirty. We are actually going to apply these processes to real data using real software and get some real meaningful results. Stay tuned.